Hi grade 12s, welcome to my channel, and let us have a look at this question and hopefully it will help you learn something. Euclidean geometry often poses a continuous challenge to a mathematician, to a maths student, and of course a fanatic like myself. But what is important here is to crack as many questions of this nature as you can, because it leaves you with a bigger chance of scoring high marks in your paper too. But higher grade questions are not always easy, not for anybody, except for when somebody has shown that particular individual how to solve those problems. Or worse, you find that it takes you a few days to figure out what to do. This clearly says if someone was writing that particular exam as well, they would have scored 0 for the question, or at least failed the question. So this is just the fun part of Euclidean geometry. It means your knowledge of the subject has to be very wide, and you need to know how to navigate each section that you have come across so far, and perhaps find a way of integrating it into Euclidean geometry, or at least apply in your approach to solving these Euclidean geometry questions. This is a grade 11 and grade 12 question, certainly a higher grade question. All right, so let's just read on and see what we can do. Perhaps before we start, I would like to propose for us to look at some notes that we need to understand before we move into this question. So what notes must we make when we deal with these issues? Now, folks, I would like to talk about what we call concurrency. All right, I don't know if it is still a topic that is taught, because the issue of concurrency to us was kind of introduced, in grade 11 as a topic of some sort, or should we say as a concept. But we have been learning issues surrounding concurrency from as far back as grade 9. I don't know how it goes these days. I'm not very much clear on your curriculum, guys, but I'm going to give you these notes anyway. Now, what is concurrency? Concurrency is the point of intersection of more than two straight lines. Okay. Basically, the definition of concurrency is more of an intersection, keyword intersection, but this has to be more than two straight lines. Again, the type of lines need to be clear. It's not just any line. It's not a curvilinear line. This is a straight line. So when we say lines are concurrent, it means more than two lines have a common point of intersection. That's the idea of what concurrency is all about. As opposed to a point of intersection when we just talk about only two lines. When there are more than two, we say those lines are concurrent. Please know this. Now, how do we apply this? Well, we look at triangles, because triangles are kind of a very interesting geometric figure, I tell you. So let's just take triangle ABC. It's an acute angled triangle. Right? Right. Now, let's just bisect. Let's bisect its corner angles. Okay, this looks like it. And let's bisect that one as well. That looks like it. Of course, it's not exactly 100%. Nope. That one is not so good. That's much better. Now, folks, if we just draw these lines, yeah, this doesn't look like what I am trying to do now. Lord of Lords. Yeah, this one doesn't look like it's a bisector. Let's take this one out. Let's try again. It should go there. That's a little bit better. It is much better. Much better. Okay, something is just trying to irritate me right now. Okay. So, folks, we will notice something. That these lines come together at that point. Remember, these lines are the bisectors of those angles of a triangle. Okay? So, what do we know about bisectors of the angles of a triangle? We know that they are concurrent, meaning they come together at a common point. Perhaps we can call this point O if we like. It doesn't matter. So what do we call that point of concurrency of the bisectors of the angles of a triangle? We know that O, maybe let's write the notes underneath. We know that O is the incenter. We call this an incenter or incenter. So this is an incenter, right? Good. So if these are bisectors of the angles of a triangle and they are concurrent about point O, it implies that point O is the incenter. But now, what do we understand about this word incenter? This is the center of an inscribed circle. Okay? In a triangle. Perhaps we can say that. Inscribed circle in a triangle. So this is an incenter. So incenter simply means the point of intersection of the bisectors of the angles of a triangle. And it literally represents the center of an inscribed circle. Again, we talk of inscribed triangle, talk of an inscribed quadrilateral. This time, it's an inscribed circle in a triangle. So what do we mean? We mean that if we draw a maximum circle in this triangle so that it is tangential to the sides, right. Okay, maybe let's just pull it up a bit. Oops, too much. A little too much. Much better. So basically, this point O represents the center of an inscribed circle. Now, an inscribed circle is the maximum circle that we can fit in a triangle. All right, great. So this is the maximum. Oh, my leg is cramping, guys. Okay, so this is the maximum circle that we can fit in a triangle. Now, note the type of the triangle this is. Note that this is an acute angled triangle. Now, the challenge to the student is to try and locate the incenter when you have, so let's just say locate the incenter in a right angled triangle comma take an isosceles triangle. Damn, this thing is irritating me now. Okay, in an isosceles triangle, and take an obtuse angled triangle, or simply just a scalene. All right, so try to locate where the incenter is going to be. Will it still be inside the triangle, or will it fall outside the triangle? Obviously it's going to be inside the triangle, right? Because the word in is already telling us a story that this thing needs to be inside the triangle. Oh God, I just said what I'm supposed to not say. All right, okay, all right, guys. So issues of concurrency are very important, because when we apply this in Euclidean geometry or even in analytical geometry, this becomes very interesting. You have seen a video on paper 2 that was written in 2005 exams. I sat for that exam. So you can appreciate the utility of the incenter. It was a huge part of that exam. And if anybody didn't know, thank God I did know. So I was able to navigate that question with ease. But not so many could see that coming. Anyway, folks, so that's very important to essentially look at what this is. So you have a task to see that indeed an incenter is inside. Let's have a look. Try these different triangles and try to do the bisectors and see where the incenter is. And of course, you will see that it will still be the center of the maximum circle that can be inscribed in that particular triangle. All right, let's charge ahead. There's a second thing that we need to talk about. Now let's take again an acute angled triangle. So we've got A, B, C. Now we want to essentially bisect the sides of this triangle. So of course this is just an approximate. Now bisectors of a triangle, they come from one vertex to the midpoint of the opposite side, okay? That's how we draw bisectors of the sides of a triangle. All right, so now we will then say this side is bisected as well as that side is bisected, as well as that side is bisected. And we can see that these come together at that one single point. So we say bisectors of the sides of a triangle are concurrent at that particular point. So maybe let's say this is ABC, say D, E, F, and maybe we can call this one H. Okay, so what do we know about this? If these lines are bisectors of the sides of a triangle, now what do we call this? We know that this would imply H is the centroid. Okay, maybe let's write this properly. Is the centroid. All right, so very important. This is the centroid of that triangle. But there's more. This would also imply that if we look at BH is to HE, we know that basically BH is to HE is going to be 2 is to 1. Very important to notice. There's many ways in which we can write this ratio. Sometimes we may want to write it in terms of the entire length. We can say HE is a third of BE, right? Or we can say BH is 2/3 of BE. Right. So there's too many things we want to say, but at the end of the day, we don't want to say too much. Okay? And in fact, this ratio can still be written as BH over HE is 2 is to 1, or is 2 over 1. So these things, guys, are very important to note and to understand, because you will also see that in my exam in 2005, this became an important part of the analytical geometry section in that exam. If anybody didn't understand this, that question would have looked horrible. It can come to you when you least expect it, because there was actually a question in the matrix of 2023? Yeah, there was something about, I think it was the May-June exams, if not the November exams. But it had something to do with some right-angled triangle that was put on the Cartesian plane. And then there was some question about a point which is equidistant from those vertices. And that was an interesting question, was it not? So you needed to know things of this nature so that you could understand what is going on. All right, so folks, again, here's your task. Here's your task here. Now find or locate. My 8 didn't come out right. So we need to locate the centroid in a right-angled triangle in an isosceles triangle, which is acute angled, of course, and a scalene triangle, or we can say an obtuse angled triangle. The question is, where is it located? We could see that in an acute angled triangle, it is inside the triangle. Of course, this would be an acute angled triangle, so it would literally be on the inside. But remember, an isosceles triangle could still be right angled. Even a scalene triangle could also be right angled. So be very careful of assuming that a right angled triangle is not a scalene triangle, or to suggest that a right angled triangle is a scalene triangle. It can still be isosceles. So what am I trying to suggest here? Is that we're just focusing on the major angle here. Acute versus right versus obtuse. Not necessarily trying to talk about the variations of a right-angled triangle, as one would have a scalene right-angled triangle, an isosceles right-angled triangle. Right. So I know what I'm saying is a little bit crazy, and it may not be very good to look at it this way, but of course this is just to pick your brain a bit and see if you can notice certain patterns, because these things, guys, they are very important. So we spoke about the bisectors of the angles of a triangle. They are concurrent about and in center, which is the center of the maximum inscribed circle in that triangle. Then we spoke about the bisectors of the sides of a triangle. Of course, these we call medians. Let me just put this word, because when I say bisectors, it sounds crazy. H is the centroid, and we need to be very clear that BE, let's list them all. BE, AD, and FC or CF perhaps are medians. Now that's another term. In fact, that's the correct term than the one I used where I said bisectors of the sides, because we are not talking the same language. There are different bisectors of the sides of a triangle. But specifically when we talk about these ones, which come from the vertex to the midpoint of the opposite side, we call these medians. Basically, a median is the line drawn from the vertex of a triangle to the midpoint of the opposite side. We call it a median. So please know these concepts, know these definitions, know these terminologies, because they will haunt you if you do not know them. So we talk about medians. So we simply say medians of a triangle are concurrent at a centroid. Now this may hold different positions, because it's not exactly at some kind of a center. As you can see, centroid, it's more like a center, but it's not at the center. So be very careful. Don't be fooled by certain issues that will haunt you here. Anyhow, we don't have too much to say, so let's just move on. Next one, let's talk about, again, we're just going to pick this ABC. Can you see here? This is acute angled, but it is essentially a scalene triangle. So a scalene triangle is not necessarily an obtuse angled triangle. Okay, so don't be fooled. So please guys, master triangles, because you have had the longest time studying triangles. Some pieces of information you probably don't know because your curriculum is deficient of the right knowledge. That's what I can say. It's not too bad. No, don't get me wrong. It's only deficient because what you guys are told to know at a particular level is ridiculous, because you should know everything there is to know about what you have studied up to so far. There can't be excuses. Anyway, let's not politicize anything at this point. So basically, if we draw a perpendicular height to this triangle, like so, and we draw another perpendicular height like so, but that doesn't look very perpendicular, huh? Yeah, sometimes the type of triangle drawn can be a disaster. How? You win. So that's a perpendicular height as well. And this already tells us that the perpendicular height to that side, of course, it's not exactly doing what I want. Okay, it's too small to select alone. But now let's pretend this is perpendicular to that side. And we see a point right where these heights or altitudes of this triangle come together. We know that altitudes of a triangle are concurrent about this point, often termed H. All right, so we know that if these are altitudes, by the way, what is an altitude? Is a line from the vertex of a triangle perpendicular to the opposite side. Just perpendicular. We don't care about how it cuts the opposite side. We only care about its perpendicular relationship. So we can appreciate that, well, if this triangle has those altitudes that are concurrent about point H, we know that point H is the orthocenter or orthocenter. Yes, orthocenter. Basically, an orthocenter is the point of concurrency of the altitudes of a triangle. Now, this is an acute angled triangle, which can be anything. Could be isosceles, scalene, whatever. We don't care. But now I would challenge you guys to specifically attempt to locate this orthocenter. Orthocenter in a right angle. What did I just do now? In a right angled triangle, isosceles triangle, or an obtuse angled triangle. Okay, try to find where the orthocenter lies in those different triangles. Please understand, isosceles can be right angled, scalene can be right angled, but I am just challenging you guys to see in a right angled triangle, whether scalene or isosceles, where does the orthocenter lies. In an isosceles acute angled triangle, perhaps that would be the best way to say it. In an isosceles acute angled triangle, where would the orthocenter lie? And in an obtuse scalene triangle, or should we say obtuse angled scalene triangle? Because we don't want to talk about an obtuse angled isosceles triangle. Because guys, this thing can be very complicated, as you can see. All right, so this is very important. I just wanted us to discuss this issue because I know this issue of concurrency has not been mentioned in many of your books. I have looked at them and I have been disappointed because these are very important concepts for foundation. Because when you study higher order mathematics, guys, that is beyond the level of matric, you will be crying blood instead of water and salt. You'll be crying blood and you will collapse because of that. Because these kind of things, if you don't know, you will be in trouble. Now let's look at the fourth point of concurrency. Which one is this? Let's take a triangle ABC again. Now, triangle ABC, we want to also section it in half on the sides. So maybe it looks like it's at the half mark, perhaps that one too, and maybe that one. Of course, I'm just using my eyes. But this time, guys, we draw perpendicular bisectors. Okay. So we're drawing perpendicular bisectors of those sides of a triangle. So I'm going to try and get it to look perpendicular. Yes, that is the one. That is the one. And let's see where does this one go? It goes right through there. Okay. So now, this one didn't come out so nice, but it is not too bad after all. So let's see, guys. Of course, this is a bit nasty now. This is a perpendicular bisector of our triangle. And that is also a perpendicular bisector. Perpendicular bisector of the side of our triangle. So we saw that, these perpendicular bisectors, of course, this is not so good. They actually are concurrent about the same point. Maybe let's call it point O. I don't really care what we name it. Point O. So we know that perpendicular bisectors of the sides of a triangle are concurrent about a point called, what do we call that point? O is the circumcenter. Circumcentor. Circumcantuar. Yeah? Yeah. So O is the circumcenter. Perhaps let's cut this a bit. I don't like it like so. Okay, I don't like this either. Let's write it on the side and say O is the circumcenter. Right. Hear the word circumcenter. What does that word mean? This is the center of the circumscribed circle. of a triangle. Okay, nice. Remember we spoke about an inscribed earlier. This one is circumscribed, meaning it's on the side. So if you look at it, if we were to draw a circle here, whew, yep, it doesn't look right, but let's try and make it look right. Okay, yeah, this looks almost nice-ish. It looks almost nice-ish. Yamos is the one. So basically, although this doesn't look exactly 100%, but this looks like at the center indeed. So we know that perpendicular bisectors of a triangle, perpendicular bisectors of the sides of a triangle are concurrent at the circumcenter. And the circumcenter is the center of an circumscribed circle. So we can easily call this triangle a cyclic triangle. So this is very important. Now it goes back to theorem 1, isn't it? Yes. What did we know? A line from center perpendicular to the chord bisects the chord. Can you see? So this whole thing links up nicely. All right, so we know that a perpendicular bisector of a chord passes through the center of the circle. Nice and easy. So this is interrelated, if not related, to what we had been doing. Of course, guys, let's just locate for you and I. You need to be able to locate. Yeah, the position I'm sitting in is crazy. But yeah. Let me try to sit well so that I can write a bit better. I know my writing is not too bad. It's not altogether bad. It's just that I am bad. Let me write like a, locate the circumcenter in a right-angled triangle. We don't care what type. Is it scalene or isosceles? No matter. But now this isosceles is such that it is acute angled and an obtuse angled scalene triangle. All right, okay. Remember, a right-angled triangle can be scalene. It can be isosceles. It doesn't matter which type did you draw. Question is, where will the circumcenter be? Interesting, if not interesting. Right. Okay, guys, so this is just the little bit that I wanted to share with you. Before we attempt to answer our question, please, I will put this question. In fact, let's just say this. Would you call it a worksheet? Yeah, whatever this is. I will put it in the description for you guys to have if you feel you need it. But you may just go on the internet. You will find all of these notes that I've just given you. So make a habit of studying further than just what you have been given. Okay, make a habit of doing that. Great stuff. Now, I would like for us to explore and deal with this question and see if what we have just done has any place in here. But remember, everything else that we know is still very much applicable. Now we start. In the diagram, AP is the diameter of a circle. All right. Now, if this is the diameter, we know that a diameter subtends a right angle. So this should be 90 degrees. And that should be 90 degrees. Right. Because AP subtends BPA or ABP, as well as PCA or ACP. So those should be right angles. So remember, every time information is given, we utilize it. O is the point where the altitudes. What are altitudes? These are lines from one vertex of a triangle perpendicular to the opposite side. So we are told the altitudes BE, where is it? BE and AK, okay, of triangle ABC. Where is triangle ABC? So we can clearly see that indeed there is triangle ABC. And let's just highlight this back so that we don't lose it. Okay, so in this triangle ABC, we can see the altitude is going that way and the other one is going that way. And so what do we call the point of intersection of those altitudes? It's an orthocenter. Great. So we know that here O, okay, let's not write it. Let's just say it. O is the orthocenter. Now we're told here O is the point where the altitudes BE and AK of triangle ABC cut each other. So that becomes the orthocenter. Great. BP and PC are joined. Great. Now we're told to draw one more line. Draw one more line. And prove the following. Now the question is, where will you draw this line? This is a very interesting question, I tell you. So where do we draw this line? Now we can see that from this statement that O is the point of intersection of the altitudes. It feels natural that we would extend this to the opposite side. Right? Right. And of course, anything drawn, we need to dash it, because a dashed line, usually I say, what do I normally say? I say this is a dotted line, but it's not exactly dotted. So this is a dashed line. So we can draw a dashed line. Maybe let's call this one K, A, B, C, D. Let's just say D. There's no D there. So we will draw this dashed line, and this dashed line will also be perpendicular. But let's leave the perpendicular part. We were only asked to draw a line. But if it is passing through the orthocenter, it simply means this line itself is perpendicular to the opposite side. It should be an altitude. But remember, this is not necessarily the construction at this point. That's a deduction. That particular point, D, or should we say the angle CDB or CDA, should be 90 degrees. Why? Because it's a line that is coming from the opposite side through the orthocenter to the vertex. It is an altitude of the circle, because we just decided to produce CO to D. And we need to say that word, produce, because if we don't say it, it means this line may be angled. So it could be something else. So strategically from our notes, we then did what we did because it felt sensible, given that piece of information, that we could do that. And let's see if it helps us at all to answer these questions. So we'll start here and say number 1. We will just say draw, or let's just say produce CO to D. That is our construction. Of course, we get a mark for doing the construction. Okay, we did that. Now what are we going to do next? Well, we have some very serious business to handle here. Now, if we look here, we now have to prove BOC, okay? It's this angle. BOC, we need to prove it is equal to BPC, which is this angle. Okay, of course, if we're asked to prove it, means they are equal. But now we need to justify this. All right. Of course, you don't want to lose this. You might as well annotate it. But remember, this is what we need to prove. So how does our construction help us to deal with this matter right here? Well, there's an issue at hand. Let me show you where the issue is. What you will notice is that we've got a cyclic quad, ABPC, because all vertices touch the circumference. Great. We know that. But now we found ourselves with a cyclic quad. Of course, we'll still have to justify why this is a cyclic quad. With our construction, if we look there, of course, I'm highlighting, guys, for the purpose of the student to follow. Otherwise, you need to see this sometimes without even highlighting, because when the diagram is too busy, it is very dangerous sometimes to highlight too much. But do you realize that we have a cyclic quad? Why? Because maybe, just maybe, we may want to showcase this perpendicularity or perpendicular situation on this side, so that conveniently we have that angle equaling that. Can you see this is the exterior angle? That's the opposite interior angle of this quadrilateral ADOE. So this already tells us we have a cyclic quad. So these are some of the things that may help us to work this out. Why am I doing this? Because I know if I take this angle and add it to angle A as a whole, I should have 180 degrees. But from my construction, I know that this angle A must be equal to that angle, right? Exterior angle of a cyclic quad. Of course, I still need to justify why this is a cyclic quad. But remember, what is this angle? It is 180 degrees minus this angle, so which gives me that. And this angle and that angle are on a straight line, COD. So they should be 180. So the 180s cancel, and guess what? That angle is equal to this angle. So this proof is going to be done like that. So we will start by saying, we've done our construction, right? We've done it nice and easy. So we will say here, essentially, once we have done this, this implies what? That ODA, order, comrades, is equal to 90 degrees. Why? We can say O is the orthocenter. Right, because this is the point of concurrency of the altitudes of triangle. Maybe let's be clear here. This is the orthocenter of triangle ABC. Because we can't just say orthocenter, we need to specify for which triangle is this, because we describe this in a triangle, at least in my knowledge. It could be that it is used to describe yet another situation in perhaps a quadrilateral, I don't know, but I only know this on triangles. Anyway, let's move on. So, establishing this, remember this was given, so we don't need to justify that part. So what are we going to say? We will say this implies that, okay, all right, okay. This implies that ADOE is a cyclic quad. Right. What's the reason for that? We know now that this angle, or maybe let's not rush because we're going to kill ourselves. This implies that ODA is equal to, or maybe let's start by naming the exterior angle. So we know that basically BEC back must be equal to ODA. We know that it's because each is equal to 90 degrees. That's why we know. So therefore, ADOE is a cyclic quad. Now this is the converse of the exterior angle of a cyclic quad, because we described the exterior to be equal to the opposite interior, and so conversely that quadrilateral should be a cyclic quad. Nice and easy. So that's something. Okay, so what are we going to say? We will say however, or perhaps let's just say but. We know that BPC plus angle BAC should give us 180 degrees. These are the opposite angles of cyclic quad. Perhaps let's not say of A, but of cyclic quad ABPC. Remember, we spoke about a different cyclic quad. We need to mention which one we are talking about. Nice and easy. So what are we trying to do? We want to describe this angle A, which is BAC, in terms of BPC. We can say, therefore, we understand that BAC is going to be 180 degrees minus angle BPC. Nice and easy. Okay, all right, okay. So now we can say here also, we understand that angle DOB should be equal to angle BAC, which is going to be equal to 180 degrees minus BPC. Right. Why is this? This is the exterior angle of a cyclic quad. Maybe let's say exterior angle of cyclic quad. We name it ADOE because there's too many of them now. We need to be specific. Otherwise, it's ridiculous when you just say cyclic quad and we let the examiner figure it out. What if they don't see it? What if you're lying? So you must prove this beyond reasonable doubt. This is like in the court of law. We are arguing here a case of this diagram. All right, folks. Now, can you see? We have been very systematic and strategic. Now we answer the question. Then we understand that this angle of ours, which is BOC, plus DOB, we should get 180 degrees. These are angles on a straight line. How do we know it's a straight line? Because we produced a line. Once we say we produce, we suggest that COD is a straight line. Here we can say either by construction or whatever we want to say, but obviously let's justify that this came from our construction as well. Can just say construction because it was not necessarily given, but now we're using it because we're asked to do this. Great. So what are we saying now? We understand that essentially BOC plus, what is this DOB? It's 180 degrees minus BPC is equal to 180 degrees. So we know that 180 is the same sign on either side of the equation. When we transpose, they cancel out. So we can make a conclusion that therefore BOC is definitely, when you transpose this, it becomes positive BPC. And we have proven the question that we were asked. So you can see this is not an easy proof by any long shot. All right, so let's mark this thing. How do we get the marks? Of course, we get the mark for the construction, statement and reason. All right, and that conclusion with its reason, very, very important. And this statement and reason also very important. And coming up here, this is very important. Right. Now, angles on a straight line, I'm not so sure. But in essence, I would suppose the substitutions here are what drives us home. So let's see, 1, 2, 3, 4, 5, 6. Well, we can make it a 7-mark question. It's not that easy after all. So these are some of the questions that can really test your patience and leave you crying and perhaps wanting to give up on doing Euclidean geometry. But remember, the harder questions you do, the more harder questions you do, the better you become at some easy ones. And guess what? The bulk of the questions you're going to come across are the easy ones. Maybe 1 or 2 difficult ones, but already your brain will be functioning at that level of the tough ones. So you should make it. You should make it. Okay, guys, you can see no small feat right there. This is a serious business. So let's get to number 2. Number 2 says OBPC is a parallelogram. So we need to prove that OBPC is a parallelogram. Okay, So OBPC. Right. So let's see, what color can we put in there? Okay, so we're looking at our diagram. We saw that OBPC is this blue quadrilateral right here. We need to prove that it is a parallelogram. And if it is a parallelogram, it means this side must be parallel to that. That side must be parallel to that. And of course, what do we know? We already proved BOC is equal to BPC. We know that opposite angles of a parallelogram are equal. So maybe this could be just as easy. Maybe it's just one of those easy questions, you know. You never know. But the mark allocation on a question like this could be the difference, because you cannot answer this for 5 marks and you just give this piece. But this is how I would answer this one. Perhaps we can say the first way we could answer it, we will then state that BOC is equal to BPC. We can say proved above. Right. From here, I can make a conclusion. Therefore, OBPC is a PAM. Why? The opposite angles are equal. Not just opposite. Well, opposite angles are equal. Because have you ever seen a quadrilateral with opposite angles that are equal, which is not a parallelogram? I don't remember so. Yes, there are some special types of parallelograms like rectangles. It's a parallelogram, but where all the 4 corner angles are equal and they're 90 degrees. Same with the square, but even more special that all the sides are equal, all the angles are 90 degrees, right? Right. And we've got a special one also, a rhombus, where it's not necessarily all angles are equal, but the opposite pair is equal, but all the sides are equal. All right? Because it's a square that is, you know, bokozas. Is it bokozed? It's bokogile. It's a bokozed square. Ish, we need to put this one in the dictionary. It's a bokozed one. Yeah, okanye botyozed. Ibotyokile. Or botyoked. Yeah, maybe let's say it's botyoked. Ibotyokile. Anyway, guys, whatever. So this one can be an easy question depending on the mark allocation. So we can say here, note mark allocation. Because it depends on a mark allocation. For me, this is a very simple question. Once I find the opposite angles of any quadrilateral to be equal, it should be a parallelogram, because I've never seen anything like that elsewhere. Okay, I have never seen that elsewhere. So, yeah, if it is a quadrilateral, that should be the one. But then let's have a look. Could we do it better and be convinced? So I think what we need to prove is the parallelity of these two opposite sides. Because once we prove the parallelity, we are good. Of course, we were given this is 90 degrees. We know this is the angle in a semicircle with AP as a diameter. So literally these two lines, the co-interior angles are supplementary. Therefore, this pair is parallel. Let's start there. We know that BEC is equal to 90 degrees. It is given. It was given because the sketch gave it to us. We know also that basically ACP is equal to 90 degrees. This is the angle in a semicircle. Okay, because we were told AP is the diameter, so that should be the one. So this implies that essentially BE must be parallel to or maybe let's put it this way. This implies that BOE is parallel to PC. Right. Did I say that? No, it's not true. Let's not rush things here. What do we want to say? We want to say BEC plus what is this? ACP is equal to 90 degrees plus 90 degrees. Be systematic, guys, don't be in a hurry. So we know that BEC plus ACP is 180 degrees. Okay, so therefore we can make a conclusion that basically BO is parallel to PC. Okay, we can say co-interior angles. My writing likes to just do this. So co-interior angles are supplementary. All right, co-interior angles are supplementary. Essentially, that's the story. But maybe let's put the E here. I think it's safe to put an E there. But all we are trying to suggest is that BO is parallel to PC in this quadrilateral. So we don't really care now about too much. So what else can we say? We can say, I don't know if we are allowed to say it, but I feel we should say it, I feel we should say it. We can say, however. We understand that now we want to prove that this line is parallel to that line. And we can see that this angle EOC or COE is the exterior angle, which means it must be equal to that, right? Right. But now if this is 90 degrees, that is that, we can actually look for this angle right there. The reason I'm looking for that angle, remember this is the exterior angle, so if we take this and subtract that, it gives us that. But you see this is also 90 degrees, so it can tell us that this angle here should be equal to that angle. And that's the case. These are the corresponding angles. Once corresponding angles are equal, then the two lines must definitely be parallel. All right, so let's do it. We can say, however, we know and understand that basically angle ABE plus angle BAC, we need to be consistent about how we called that one, should be equal to angle BEC. Right, what is this? This is the exterior angle of triangle. We name it ABE. Nice and easy. All right, so what does this imply? It implies that we want this angle ABE plus BAC, which is not a big deal. What did we call BAC after all? At this stage, I'm not interested in BAC being equal to, PC and what. I'm really not interested. It really doesn't help me at all. Of course, we can use it perhaps to stay consistent. BAC, we said it's 180 minus BPC, but I mean, it looks like we're complicating matters. I really don't like to complicate matters here. Let's not put the values. This is just BAC equal to BEC is 90 degrees. We can say, therefore, ABE should be 90 degrees minus BAC. Okay, number one. So we can say here, also, what do we know? Maybe let's continue in the next page. We can say here also, we know that basically ABE plus, say, OBP, right? OBP is equal to 90 degrees. Why? Angle in a semicircle with AP as the diameter, right? Or we can say opposite angles of a cyclic quad, with this being 90. From 180 we take 90, we remain with 90 for the other one. So there's many ways we can do this. So what are we trying to get to, folks? We are trying to look for OBP. So what are we going to say? We are going to say this implies that OBP is equal to 90 degrees minus ABE, which also implies that OBP is 90 degrees minus, this is 90 degrees minus BAC. Therefore, OBP is equal to 90, and 90 goes away, negative, and that, okay, BAC. Holy cannoli. Now, can you see this one? OBP is this lovely angle right here. Is this lovely angle right here? Let's use another color perhaps that will make it look interesting. So this is that angle. So this is equal to BAC, which is that angle right there. Since we used the black color, maybe let's maintain the black. I went. Alright, so this angle is equal to that angle. Very interesting. Alright, we will say then, okay, now this one is a long essay, a very long essay, a tiring essay. So I'm trying to see, guys, what must we do now? Okay, we will say then, let's just answer the question. Then we understand that COE is equal to angle BAC. What is this? This is the exterior angle of cyclic quad. What was this one? The one that we got, it was A, D, O, E. So what do we see now? We can make a conclusion that therefore OBP is equal to COE. Right. Therefore, we can conclude BP must be parallel to OC or CO. Again, what do we know? Corresponding angles are equal. So this could be an essay. What are you doing? This could be an essay. Is it SA or essay? Ngiyahleka ke manje uma usuxakane nesilungu. Akusiyinkinga yami leyo. All right, folks, let's have a look. Now, this one was a nasty essay, even nastier than the first one. When we look at it in terms of the parallelity, now we can easily say, therefore, we can therefore conclude that OBPC is a PAM. Right, we know that BP parallel to OC and BO, this time we're just going to write BO parallel to PC. All right, so once we have a set of opposite sides that are parallel, this is a parallelogram. So again, let's see how many marks one should get if this is the proposed approach. This is crazy after all. This is a mark proving that the opposite angles are supplementary and essentially justifying why we are saying that line is parallel to the other. But perhaps I'm giving too many marks. Maybe I'm giving too many marks, but I do feel this is very important. Yeah, 3 marks there. And then the exterior angle of a triangle, but perhaps the mark is more on the answer than the rest of the statements. So that would be 4 marks. And then this one is a key statement, 5, and then 6. Hey, wena man. Yeah, guys. 7, 8. Hi. 8. Yeah, this is a lot. This is a lot. But since we spoke about the cyclic quad, I don't think this is too strong. No, man. So 1, 2, 3, 4, 5, 6, 7. So, of course, if here the proposal was that this question is 7 marks, you would certainly not answer it this way. But if this was 2 marks, definitely that would be the answer. But I do believe there's no need to suffer like this. This would be the one. But of course, for 7 marks, guys, be very careful. Certain answers are very obvious and easy. But you're not going to get 7 marks for just this statement right here. No. That already is saying the examiner has a different idea. The examiner is walking a different path and is suggesting the same for you. So certain questions are nice in that you can answer in an instant, but they can come in a very horrifying way. All right, okay, all right. So that's it, guys, for that particular question. Now we're supposed to do number 3. Now, number 3, folks, I can tell you these are the questions that would be marked 2 to 3 asterisks because, wow, they are horrible. But you can see all these questions are horrible. This question was already 2 asterisks on its own. Okay? I'm sure you can appreciate that. Now we need to prove that AP squared. Of course, we've got a triangle APC, which is right angled. Maybe we can use that. AO squared. AO squared is the hypotenuse side of this triangle ADO or AEO, whatever. So there's 2 triangles that AO squared can be written from. And then BC squared. BC squared is the hypotenuse of this triangle ECB. It is the hypotenuse there. Or it could be the hypotenuse of triangle DCB. So this question is troublesome. Is troublesome. But what I'm appreciating though is the overlap of the hypotenuse. Because this BC, we can look at it in terms of this, right? At the same time in terms of that. But I don't know, there's just too many things that are going to get in the way. Let's just have a look. Let's just have a look and see if we can win. Yikes. This question, hi guys, no man. I don't know what to do. Anyway, let's just look in triangle. Let's say APC. We have already stated that this is 90 degrees. Did we? I don't think we used this part. Let me see. Did we describe ACP or PCA? I don't think so. We never spoke about it. Okay, I called it ACP. Yeah, we did speak about it, that it's 90 degrees. So, yes, we know that from this triangle, we know that AP squared is going to be AC squared plus PC squared. Now the question is, can we change any one of these two into these? It's either this goes there, or it goes there, or that goes there, or it goes there. We don't know which one. Can we do it? Because we know also that AP squared is equal to BP squared plus AB squared in triangle ABP. Because again, we described that angle as 90 degrees. So this would be Pythagoras. Maybe let's state clearly that this is Pythagoras in this triangle. So Pythagoras in triangle ABP. Right, so same story. Could this go there or there? Or could this go there or there? Yeah, ne? Aziyakhala. Holla siphadi jwale, holla phafa. Ha ke tsebe ke nngwe taba. Ho thata ha o le tjena. Ho potlaka ha o thuse ka nix. Tshwanetse hore o iketle. O nke nako ya hao. O nahane, o shebe. It's difficult, guys. Does this parallelogram help us in any way? Because sometimes what we proved can be the source of help. Yeah. I don't see it. Maybe it will. It surely should come into play somehow. But I don't know. There's a lot, man. There's a lot. So let's see. BP squared is going to be this minus AB squared. And then AB squared is AE minus BE squared. And then BE squared and EC gives us that. EC and OE. Oh, here one. Remompieng piano. Remompieng. Waitsebamphia. Awuthi ndilalele ngecala. Andisawazi nokuba mandithini ngoku, guys. Yabona ke phapha. Ndiye ndaniphaphe lapha ndaza nee-questions ezimnandi ngoku ziyandikhalela nam. I don't see, guys. Can you see what we need to do here? Because you see, my problem is that taking this triangle, it doesn't really help, because look at this. We've got BP squared, which is fine. We see where it is. And then we've got AB squared, which is the hypotenuse of this triangle. You know? And then when we describe AB, if we try to describe AB in terms of triangle ABE, AB squared is going to be basically BE squared plus AE squared, right? Right. This is Pythagoras in triangle ABE. Okay, we're getting somewhere, I hope. Now, there's this dude. How do we deal with this? Because even this one is nothing close to what we want. BP squared. Well, since this is a parallelogram, right? We can take this BP and represent it as OC, right? Right, so we can say this is OC squared from OBPC parallel. Okay, maybe this is crazy now. Let's say from parallelogram OBPC. Okay, so literally in here we've got OC squared plus BE squared plus AE squared. So it looks like we're working here. All right, so let's just keep going. And now we've got OC squared. OC squared, OC squared, we can see that in this small triangle, OC squared can be EC squared and OE squared. But does this EC help us? Doch. Okay, let's just keep going. We don't really care anymore. Sometimes when the question is this crazy, guys, you need rough work. That is a skeleton, but be very strategic so that as you keep going, you just keep seeing where the links are, and then you're gonna write this nicely in the answer sheet. Okay, so now we're just brainstorming the solution. How does this EC help us? We saw that EC is part of this BC squared, which is what we want as part of the solution. So let's let the EC comes in. So OC is gonna be OE plus EC squared. Okay, again, this is the Pythagoras in triangle OEC. All right, so what do we end up with now? We end up with OE squared plus EC squared plus BE squared plus AE squared. Okay, now we can see once we get this mess, we need to group here. So think of factorization by grouping. So we may have to strategically group things together. Okay, anyway, let's have a look. OE, what I like about OE, it introduces us into this AO, essentially. AO, and there's AE there. Yes. If we take OE squared and add it to AE squared, can you see in this triangle, AE squared plus OE squared represents OA or AO. Okay, so we can see that these two bring about AO squared, right? And then these two, they should give us something. EC squared, let's see, EC squared plus BE squared plus BE squared gives us BC squared. Nice. So iphumile. Yay, hayi khona. Imaths iphambene bantwana besikolo. Ndiyaqale imaths ayidlali. One of these questions are hot. Yeah, they are very hot, guys. So, hey, ubonile na ukuthi ayizi straight le mpendulo. So we know now that this is what answers our questions. We will need to group things. We just keep moving from one to the next. So literally we're going to start in this triangle ABP. Okay, so you can see the final construct is a bit strange. So we will say, so what I'm going to say, because we are systematically moving from triangle to triangle, I'm not even going to say in triangle. I'll just say AP squared is equal to BP squared plus AB squared. Okay, this is the Pythagoras theorem in triangle ABP. All right, which implies that AP squared is equal to, and then we saw that BP squared is the same as OC, right? Right. Opposite sides of a parallelogram. So you know what I normally do? I will just put it in here and then justify what I'm doing. You know? Justify what I'm doing. Okay. Let's try to be a bit systematic here. We will say here, but we know that BP is equal to OC. How do we know this? These are the opposite sides of parallelogram OBPC. And we also know that AB squared maybe let's just say also AB squared, as we did it here, is equal to BE squared plus AE squared, right? Which is Pythagoras theorem in triangle ABE. All right, so we're saying things here. We'll say this implies that AP squared is equal to, instead of BP, we're going to write OC all squared, because we just show the substitutions, plus instead of AB squared here, what are we going to write? BE squared plus AE squared. The brackets are just there to showcase that we are now substituting those two things into our main equation. Yeah. This thing is what. And we saw that all we needed was to just then work out OC. Okay? Because once our BE is in order, we just work out OC, which also implies that AP squared is equal to OC squared. Let's get the brackets out. BE squared plus AE squared. Okay? Now, we will say, however, we know that OC, did we say OC? Yeah. We know that OC squared is equal to, remember we said OC squared is going to be equal to OE squared plus EC squared. This is Pythagoras in triangle CEO. The Chief Executive Officer. So if this is the case, it implies that AP squared is equal to, instead of OC, we will write BE squared plus AE squared plus BE squared. I. What the hell now? What the hell? What is this now? Damn. Wait a minute. What is this now? So this is OE squared plus EC squared, okay? Plus BE squared plus AE squared. Nice and easy, which also implies, so guys, be systematic. Remember, you learn by observation. This is why I'm showing you these things, because I know you will not know how to do these things if you did not see somebody do these things. And this helps to unleash your talent, because you already have a talent to even see beyond what I'm doing, maybe even finesse what I'm doing. Anyway, so we saw that technically we needed to group things here, because if we group these things nicely, we saw that OE squared plus AE squared literally are going to move us into this triangle. Since this is 90 degrees, angles on a straight line, that will give us 90 degrees. So we will be good. So this is a bit cumbersome otherwise. We just want to showcase our grouping. So we will say this implies that AP squared is equal to, now we will take OE squared plus AE squared and group them together. Say plus. Now EC plus BE squared. We group them together. And then we will say, then, Buffets. Okay, I'm trying to think now. How do we make sense of this situation? This is good, but I wanted to say something about this triangle. So I've used but, I've used also, I've used however. Okay, maybe let's answer the question. You know almost how I do it? I say then, in triangle AOE. What did we call that triangle? Did we even talk about it? Never. We did not. So in this triangle, what do we know? We know that angle OEA plus angle BEC, we should get 180 degrees. These are angles on a straight line, right? Which implies that OEA plus 90 degrees, because that was given, is equal to 180 degrees. Therefore, angle OEA is equal to 90 degrees. Remember, we need to show that that is 90 degrees. So everything we do, we justify. Please, don't be hooligans and don't assume the examiner knows what is going on. We can say here safely, this implies, we can say, therefore, we know that AO squared is equal to OE squared plus AE squared. This is Pythagoras. Right? Yeah, this one was crazy. Therefore, I don't know, guys. Maybe there's too many of these. If this is the case, it implies, yes, Yafiwala. This implies, let's try to do this better. We know that this is the case. Okay, guys, now I'm stuck with my own creations, but I want this to flow. As you can see, it's not so bad once we know what to do, but I want it to flow. How do I say what I want to say? Oh yeah, if this angle is proven to be 90 degrees, we can also conclude for the other triangle because they share the common angle there. So we can say also, therefore, also AB squared is equal to essentially AE squared. Imag. Something is not right. Something is not right because EC squared. Oh, yeah. And BE squared. They give me this BC. So that's what I want. So why am I bringing the AB again? I don't need AB. No. I don't need AB. I need BC. BC squared is equal to BE squared plus EC squared, right? Pythagoras theorem in triangle. This is BEC. I don't know if we spoke about it anyway. We probably did not, but it doesn't matter. So, yeah, guys, so what can we say? After this, we can conclude that. Yeah, guys, there's too many conclusions, but it doesn't matter. AP squared is equal to this group. OE squared plus AE squared gives us AO. Plus, we saw that EC squared plus BE squared. This is not G, it's E. Okay, so it gives us BC squared. Yeah, doch. That's a nasty question. But I'm sure you can see, guys, that strategy always works. Sometimes when you're not sure what to do, you just look at what you have and play around it and see where it leads you. Okay. So let's see how many marks would one get for such a question. And as you can see, the main question was answered here. So that should be a mark. This is a very important mark. Yeah. Yeah, guys, there's just too many areas here. There's just too many areas. But for me, everything is good up until here. Okay? This one was too obvious. I don't want to end up giving too many marks. Now, defining OC as well is a bit key. And then this substitution doesn't really matter now, but what matters is this grouping. So 1, 2, 3, 4, 5, 6, 7, 8, and of course this one, as much as it is perhaps mark worthy, but I think 8 marks is fair. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I think 8 marks is fair. So guys, I'm going to attach the I'm going to attach the question with the notes and this answer sheet on the description. This was a long video, of course, but the intention is to just try and expand your knowledge, guys, and to show you the strategies that you may use to answer complex questions using, basic principles that sometimes at this stage you are starved of, because I doubt your teachers teach you these things. If they do, good luck to you. And in fact, congratulations to have the best teachers. But if you don't have, well, if you have come across my channel, consider yourself a bit lucky, because not entirely lucky. I am more of a blessing and a curse at the same time, because yeah, what I may do may offend your teachers, and then they may look at you as someone who's trying to prove a point, and perhaps they may victimize you. But here's what I can tell you as a student. If you learn something strange, something rather interesting, and perhaps even good, when you ask your teachers about it, pretend as if you are not so sure about it, okay? Don't come out with so much confidence in that this is, just say, but I think I came across something like this, but I'm not so sure if it applies here. Although you know it does apply, just pretend you're not so sure. Make the teacher feel in control, and that they should be the one to approve of what you're bringing. Don't say, I watched a video on YouTube and then there's that dude, he said this, and so say you are wrong. Then say he's going to be offended and be like, who is that somebody talking about? Is he even a teacher? The reality is he is not. And then they'll say, rubbish, it's not in the exam guidelines, don't take it. And then you'd be so confused, because you will have understood what I'm saying. You will have seen its utility, but then you may find yourself not so sure of when and why you should use it, because your teacher may discourage you. But guess what? In the next exam, you find a question where this applies, or even a similar question where you can solve your matters this way. Then you're so not sure because your teacher was not so happy about it, and then you'll be thinking the markers wherever your paper is going to be marked are not going to be happy. And then you shy away and you lose marks that you would have scored, because when the memo comes, it's exactly what you saw. I showed you. So here's what I'm trying to say to you guys. If you learn from me, be very careful. I make mistakes, okay? If you're not so sure of what you see, please just ask the question. As ridiculous as it may sound to you or to anybody, it is good, because I need to confirm that I am saying what I'm saying, especially when you're not so sure if what I'm saying is what I'm saying, okay? Once you understand what I'm saying, once I've elaborated as to what I was trying to say, if I made a mistake or if I confirm that this is exactly what I'm saying, read around it. Then when you present this as a way of solving a problem in your classroom with your teachers, or in your scripts with your teachers, always pretend to be the guy who does not understand but has this idea, okay? Believe me, your teachers are going to love you. And in fact, they will start to place you higher in the class, because they know you are the think tank, as your lousy politicians say. They once said somebody's a think tank, and all of a sudden he's no longer a think tank because he's no longer with them. So you can see how much of flip-floppers those bastards are. They irritate me. If I was to be a vigilante, I would kill all of these loud mouths in this country who just cause nothing but divisions. Anyway, let's leave those fools to just keep fooling around until they themselves end up just as foolish as they think we all are. Now, that's just me, guys, giving you tips on how to present your newly found pieces of information that are certainly good and useful. But just go to your teacher but say, if I think of it this way, would I be wrong? And you know you are right, by the way. And you know your teacher is wrong sometimes. But whenever your teacher is wrong, don't say you're wrong. Just say, could it be possible for me to solve it this way? Does this concept apply the way I'm applying it? Let the teacher think. Let the teacher feel in control. Don't embarrass your teacher in front of your peers as well. In fact, don't go around, boasting that you know better than your teacher, or somebody else you saw on YouTube is better than your teacher. I see a lot of you guys in some comments on some videos that I come across, of very good presenters, by the way. You keep saying, my teacher, this cannot do this. Remember, you are stuck with your teacher. Your teacher, in many ways, determines your future or influences your future. So do not disrespect your teachers, because your teachers also come across these videos. They will see you and see the rubbish comments you write, and then they will take you down in the next exam, because every mistake you commit, they will eat you alive over it, because they will be trying to make sure that they prove a point that you're not just as good as you think you are. And yet, if you are humble, you present whatever you find the right way. Even the comments, they need to stop comparing your teachers with your tutors on YouTube. Even just stop doing that. Stop saying so-and-so is better than so-and-so. Of course, just on face value, it may sound as such, but do you even know what those people have combined together? Because some people, they don't solve these things de novo, as I would call it, or on the fly. They first look at the memorandum somewhere, and then try to create some ways of, running around the memorandum so that they may look and sound smart. But those are pre-worked issues. So would you really compare your teacher with somebody who already has a pre-worked thing, and then they are showing you that? Because who's going to show you the memorandum during the exam? You see that? You act on the fly. They don't. So stop comparing. But I'm not saying they are wrong for doing that. They are actually right, because remember, they need to give you these pieces of information within reasonable time, because again, data and many other things. You also don't have 2 hours, as I'm going for 2 hours right now, to say what I'm saying. Because my videos are boring because they take forever. But remember, these are for students who really want to make an impact, not just in their lives, but in many of those around them. Because if you don't have an all-rounder type of knowledge and understanding, insight, and everything, tricks, tools, everything, man, put together, you will not be the best. That I can assure you. You will just be one of those who made it, but will never be the best. That's just the thing. So my videos are geared for those who really want to be part of the best, and perhaps one of those will never forget ever existed. That's where I'm trying to push you to. At the same time, I'm taking one who would not be looked at as someone who has a potential. I'm converting you to someone with a potential. Because once you show some of the gymnastics I'm showing you, no one would not pay attention to you. And in fact, they would not ignore you. But be humble about it, as I have shown you. If you want to suggest an answer to your teacher, perhaps they're solving a problem you've seen me solve, and now you know what to do. Don't say that's wrong. Just say, could I be wrong if I'm thinking of it this way? Does what I am saying apply perhaps in this question? And could I then be marked correct if I have solved it this way? Perhaps you are suggesting an alternative of solving a problem. Perhaps you are correcting a teacher who's actually wrong because they looked at the memorandum that is also itself wrong. But then no one is going to pick that up, because we always assume the memo is correct, but it's not always the case. Okay? So folks, that is the idea I'm trying to plant in you. That be humble about your knowledge that you acquire. Please don't compare people, because how they do things is not exactly what you think. I could have made this video to be perhaps a 45-minute video by just making sure that I fix my video to move faster, perhaps in certain sections, like when I'm explaining these. I could make it faster, by editing my video now. I'm going to give it to you raw, because I want you to see everything I'm doing, because I do these things on the fly. Why? Because you also do these things on the fly. In the exams, you see a question on the fly and answer it on the fly. You don't go and read the textbook and check the concepts first, see and wait. I may take 2 hours to solve your problem that you're going to write in the exam because I don't have the pressure. No one is marking my script. I have all the time in the world. You don't. So the reality is you need to be shown how to do things on the fly, because that's exactly your exam situation, and exams are what counts. Classroom work and lessons and tutorials, those are open book exercises. They are just there to build a foundation. Don't be fooled by them. But what matters is someone who solves problems on the fly and shows you their thinking, their patterns, putting things together, and that takes time. Now I'm trying to show you that it takes very long to do these things, but I can assure you, with the right knowledge, the right ability to see and connect things, you don't need to be like me. For me, my duty is to show you a complete picture in the best way possible. But you guys, sometimes you will see your memos also cut the corners. So you will start to see what you want to cut out. But I just want to make sure you present your answer in a way that can be understood by the person who's marking, even if that person is not so strong in the subject. But once you are clear and you direct them as to where you are looking and why you are looking there and how everything links up together, you will be the person no one can ever forget. And in fact, you will find yourself getting marks that you did not necessarily get because of how very good you present your work. Anyway, guys, so that is it for me. I've spent the 2 hours that I hoped to spend with you during a lesson to try and fortify your efforts in Euclidean geometry by perhaps presenting this issue of concurrency, because many people ignore this, but it may very well apply in your next exam. You never know. Yes, it may not be part of your exam guidelines, as you are often told. Exam guidelines, exam guidelines. Yeah, it's a good idea. Believe me, it's a good idea to have a look at the exam guidelines, because at some point when you have a topic that you don't understand and you don't know what is important in that topic, the exam guidelines will give you the bare minimum that you can do to still survive the section. And at first, in fact, not at first, but what was I trying to say? See the English language, man. And in essence, yes, I wanted to say that in essence, when you look at guidelines, you'll find that guidelines are more of a summary of a topic in a way. Because if you follow guidelines, in many ways, you start to find an angle of how to approach a topic in terms of a textbook standpoint, how to read, what to focus on, which definitions seem to stand out. Because the moment you use your guidelines as your baseline, it already puts you in a good position, because you start to figure out how to approach a topic. From there, you then read further. Don't limit yourself to guidelines. They are just the minimum requirement. Believe me, they are not the ultimate. They are just a minimum requirement. It means a student who sits for an exam should at least be at the level of the exam guidelines in terms of performance and understanding, and of course the gymnastics. But you will see that questions of this nature can pop up, and no guidelines are going to help you. Okay, let's just say not necessarily are they going to help you. You will have to help yourself. Anyway, guys, but here's what I was trying to say. You learn by observation, okay? And teachers need to employ what we call operant conditioning to kind of, set some way of doing things depending on certain things, okay? that you are going to be exposed to, and as a result, once you see them, you know what to expect. On top of that, we need to employ some principles around it, which is reinforcements. We need to do positive reinforcements when people show effort and eagerness. We also need to punish when bad behavior and bad habits start to showcase in their writing of their answers or behavior in class whatsoever. We cannot use this nonsense of saying you need to understand, you need to talk to people. Sometimes that is what makes young people to lose focus, because their parents become literally their friends. And you cannot turn a classroom into a circus. I know a lot of people like to crack jokes. I do crack jokes too. But I hate it when people teach in a joking manner. Sort of like the entire class is just a joke. You know, they recite recitations like they're back in kindergarten or something, or elementary school. And yet they're trying to teach professionals of tomorrow. Like, how could you teach matriculants like that? Really? Would you be stating things in a recitation form because you feel this is the way they would understand you better? I mean, these are not children. These are soon to be adults. They're essentially young adults. You cannot speak to such people like that, because who are they going to talk to like that? Who are they going to present their work like that to? Really? No, man. I know, you want to make subjects fun. Now, this is for the tutors and the teachers, of course, because for students, it's not really good. But again, I want to make sure that students don't fall for this nonsense, because a lot of people, they just turn a classroom into a circus. Everything is a joke. I mean, that's not how you learn mathematics. I promise you, if you learn maths like that, you're going to fail, because maths doesn't smile with you. I mean, look at these questions right here. Look at this question, actually. It doesn't smile with you. There's no jokes you can crack about this one. And if you're not focused, you rely on jokes. Jokes can only work for simpler questions. But again, that's just a bad way of teaching. So teachers must not be, students' friends. No. Kids need to fear the teacher, actually, so that they can do the work and put in the effort. Otherwise, when they know the teacher is okay, even if they didn't write the homework, they will only do it conditionally. When they don't know, they will not put an effort. They won't study so that they know. They will just say, I don't understand this one. I just don't seem to get around it. Okay, guys. So anyway, please, if you are a tutor or you're a teacher and you come across my videos, I know I come out as arrogant at times. And I sometimes, I'm crazy, I guess. Perhaps a lunatic, if you will. And I'm very obnoxious, by the way. I'm one of those not so nice individuals in the world. I'm not very palatable. I am bitter, like alkaline. All right? And I corrode. If you swallow me like that, you gotta dilute me before you can swallow me. You're not gonna swallow me raw. I'm gonna disintegrate your esophagus. I'm the acoustic injury. I dig deeper and I head, okay? So that's me there. So anyway, folks, I'm just joking with you anyway, but technically speaking, I'm actually telling you the truth. Anyway, folks, I hope you enjoyed the video and you are going to love it. I know this is one single question, but we ended up with 2 hours of work. And I'm feeling like, no, man, it's not regi, but yeah, you deal with it. It's not my problem. I'll see you again next time, guys. Bye-bye.